The birth of quantum mechanics, action at the heart of a scientific revolution. The 20th century saw a scientific revolution with the birth of quantum mechanics, and at its core was the concept of action. Surprisingly, it all began with electric lighting in Germany. In the 1890s, electricity was becoming more widespread, at least in urban centers, and electric light bulbs were the hot new innovation. Germany sought to replace all its gas street lights with electric bulbs, which raised an important question: how could scientists maximize the visible light emitted by a hot filament? Researchers at the Physikalische Technische Reichsanstalt (PTR) studied how different materials emitted light as a function of temperature. At lower temperatures, each material emitted a characteristic spectrum, mostly in the infrared. But above 500 degrees Celsius, all materials emitted light with a nearly identical distribution. The hotter the object, the more energy it emitted at every wavelength, with the peak shifting toward shorter wavelengths. However, scientists still didn't understand the theoretical principles governing this behavior. Understanding it could enable better lighting designs, so they sought a theoretical framework. The Blackbody Problem. To simplify the problem, researchers imagined an idealized object, one that would absorb all incoming light and emit radiation purely based on temperature. They conceived a hole in a metal cube, which acted as a perfect blackbody. Any light entering would be absorbed entirely, and any radiation inside could escape through the hole unimpeded. Physicists theorized that electrons in the cube's walls would oscillate, emitting electromagnetic waves. These waves would reflect off the walls, interfering with each other to form standing waves, waves that appear stationary due to interference. Given enough time, only standing waves would persist, while all others cancelled out. In a three-dimensional cavity, the number of possible vibrational modes increased with the cube of the frequency nu3 / nu3 nu3 or 1 lambda 3 1 / lambda 31 lambda 3. The assumption was that at shorter wavelengths, higher frequencies, the number of modes would grow indefinitely. This led to the Rayleigh-Jeans law, which matched experimental data at longer wavelengths but disastrously predicted infinite energy emission at short wavelengths. This paradox was called the ultraviolet catastrophe. Planck's radical solution. Max Planck ultimately solved this problem, but his path to discovery was unexpected. As a teenager, he had considered studying physics, only to be told by a professor that physics was essentially complete, only minor details remained. Fortunately, Planck ignored this advice. By 1897, he was a professor himself, struggling to explain blackbody radiation. After years of failed attempts, he was willing to abandon all previous assumptions about physical laws. In what he later called an act of desperation, he introduced a revolutionary idea: energy could only be emitted in discrete packets, or quanta. He proposed that the energy of each quantum was proportional to its frequency, E equals hf, E equals hφ equals hf. Where hhh, now known as Planck's constant, is a fundamental constant of nature. This quantization drastically altered the predicted spectrum of blackbody radiation. At low frequencies, quanta were small enough that all atoms could emit them, aligning with the Rayleigh-Jeans law. However, at high frequencies, quanta required more energy than most atoms possessed, preventing infinite emission and resolving the ultraviolet catastrophe. By fine-tuning hhh, Planck's formula matched experimental data perfectly. However, he was troubled. His approach felt like a mere mathematical trick. He had introduced a new constant without understanding its physical significance. Determined to find an explanation, he later reflected, "After some weeks of the most strenuous work of my life, light came into the darkness, and a new undreamed of perspective opened up before me." Einstein and the quantum leap. Initially, Planck's idea received little attention. That changed in 1905 when a 26-year-old patent clerk named Albert Einstein argued that Planck's theory wasn't just a mathematical convenience, it was physical reality. Einstein proposed that light itself consisted of discrete packets, later called photons, each carrying energy E equals hf, E equals hf, E equals hf. He used this insight to explain the photoelectric effect, the phenomenon where light ejects electrons from a metal surface. Crucially, Einstein's explanation revealed that only high-frequency light above a certain threshold could cause electron emission, regardless of intensity. This contradicted classical wave theory and firmly established the quantum nature of light. Bohr's quantum model. By 1913, Niels Bohr sought to explain why electrons orbiting a nucleus didn't spiral inward due to radiation loss. Inspired by Planck's quantum idea, Bohr proposed that electrons could only occupy specific quantized orbits, where their angular momentum followed the rule, L equals nh2 pi L equals n backslash frac h2 backslash pi L equals n2 pi h. Where n is an integer, and equals h2 pi backslash bar equals h2 backslash pi equals h2 pi, known as reduced Planck's constant. This assumption, though seemingly arbitrary, led Bohr to derive the correct energy levels of hydrogen. His model also explained why atoms emit light at specific wavelengths. Electrons could jump between quantized orbits, emitting or absorbing photons equal to the energy difference. Though successful, Bohr's model lacked a clear explanation for why angular momentum should be quantized. That answer came from an unexpected direction. De Broglie and matter waves. In 1924, French physicist Louis de Broglie took quantum theory further. He reasoned that if light could behave as both a wave and a particle, perhaps matter could as well. De Broglie proposed that any particle has an associated wavelength, given by lambda equals hmv backslash lambda equals backslash frac hmv lambda equals mvh, where mmm is mass and vvv is velocity. For electrons in atoms, de Broglie's idea meant that their orbits must correspond to standing waves, just as standing waves in a musical instrument require whole number wavelengths to fit within the length of a string. Applying this to atomic orbits, he derived 2 pi r equals n lambda 2 backslash pi r equals n backslash lambda 2 pi r equals n lambda. Substituting his wavelength formula, he found mvr equals nh2 pi mvr equals n backslash frac h2 backslash pi mvr equals n2 pi h, which exactly matched Bohr's quantization of angular momentum, finally providing a physical reason for it. The double-slit experiment and quantum weirdness. De Broglie's insight had profound implications. If electrons behave as waves, they don't follow single trajectories like classical particles. Instead, they must explore all possible paths. This became strikingly clear in the double-slit experiment, where electrons fired one at a time through two slits form an interference pattern, as if each electron somehow passes through both slits simultaneously. A famous classroom anecdote illustrates the depth of this idea. A professor explains that the probability of finding an electron at a certain point on a screen is determined by adding up wave amplitudes from both slits. A student asks, "What if you add a third slit?" The professor replies, "You just add that amplitude too." The student continues, "What about a fourth, a fifth?" Eventually, the professor, losing patience, concedes, "You just sum all the amplitudes from all possible paths." This simple question captures the essence of quantum mechanics. Quantum objects do not take a single path, they take every possible path simultaneously. From Planck's desperate gamble to Einstein's photons, Bohr's atomic model, and de Broglie's matter waves, quantum mechanics emerged from a series of profound and often counterintuitive discoveries. and at the heart of it all was action, the mysterious fundamental quantity that dictated nature's quantum rules. This revolution in physics continues to shape our understanding of the universe, proving that even in science, the smallest steps quanta of action can lead to the greatest leaps.